were talking about RC circuits last week. So I finished the charging phase of RC circuit. So let me explain quickly what is RC circuit. RC circuit is the one that has circuit that has both resistor and capacitor. R is the representation for resistor, and you have C as a capacitor. Okay. So this is the circuit. You have a battery like that. So the battery of EMF E, that is the source for the current. So this is a switch over here. The capacitor. As soon as you turn on the switch over here, basically the current pass through the resistor and capacitor. Okay. So you have a charging case that we learned in last lecture. It's a charging case. So over here, the charging case is defined such a way that if time t equal to 0, where you turn on the switch, okay, and then the capacitor has 0 charge. T equal to 0, whenever you start the time, set the time, charge is 0. Okay, and if you wait for a long time, t equal to infinite, I mean long time, in the physics we call it infinite. Okay, then the Q final you can call Qf is maximum. Okay, Q0 is a maximum charge. It's a maximum charge. So this is the behavior that so your capacitor is charging off. Okay, it's charging off if you go like wait for the time. Okay, it's called charging case, and we learned about that, charging case on the last lecture. The charging case of the RC circuit is very similar to your power bank. It's exactly power bank, where you have you have a capacitor. If you want to go for hiking or like camping or something, you charge your capacitor, backup, right? And make sure that your backup is full. That means now you don't have to have this part. So this is the charging. You have a battery. Now your capacitor is fully charged. Now your power bank. Okay. So let me draw another diagram. You have the same circuit, but I want to draw the discharging case. Okay, you have a battery and you have a switch. So and you have a R. So exactly the same. So this is the battery. That external battery is the driving force whenever you charge. But once let's say you have a switch 1, okay, you used to charge the capacitor. So now, as soon as your capacitor is fully charged, so now you can disconnect this one, okay, and you can have another switch over here, S2, let's say. You have a switch, another switch, okay. This is S2, switch 2. Now, you basically turn on this switch. So you only focus on this part because now your battery is disconnected. Your battery has no role at this moment because the current from the battery doesn't flow because this is the open circuit over here. Now your current, your battery I mean, your capacitor acts as a battery. Your capacitor is like now battery because the power bank that you have acts as a battery, and the current flows from this direction. Okay, the current. This is the fully charged. Okay, your capacitor is fully charged. Okay, you have a potential across this capacitor, and that provides the current. And this resistor, it can be either a cell phone, or it can be your light bulb. You can use that backup for lighting up. Whenever you go for camping, you can use a small LED lamp. And then you can light up during the camping. Okay. So basically, this is the battery now. The capacitor acts as a battery source, and this R can be their filament from the like a light, or you can charge yourself. Okay. So now you have fully charged over here. The capacitor is fully charged. Okay. So now it's a discharging case. Number 2, discharging case. So discharging case of RC circuit case. Okay. So over here, at t equal to 0. So at time t equal to 0, your capacitor is fully charged. Okay. So you have Q is maximum charge. Okay. You have Q0 is maximum. And if you wait for a long time, if you use up your backup for a long time, your capacitor will be empty of charge. There will be no charge over there. You use up all of the charge, okay, to 0. Okay? So power bank acts as a battery over here. You can study this one in terms of potential also. If you want to talk about it in terms of potential, the potential across this one is maximum. Okay? CE, like a CE, maximum value, and BC will be 0 because there will be no charge, it will be 0. And you can talk in this out. BC will be 0 in the beginning, BC will be maximum C times C, maximum value. So this is like a behavior of RC circuit in a discharging case. We can study, in terms of the graph. We can again use the differential equation to solve it. So over here, how the charge is a function of time. So this is t time, and this is charge. Okay. So at t equal to 0, your capacitor is fully charged, Q0. And if you wait for a long time, the charge will be 0, right? So over here, Q can be, the Q is a function of time, can be explained Q0 e power t over tau. Tau is the time constant, given by RC. This is the behavior of a charge a function of time for discharging case of RC circuit. And definitely you don't have to memorize this formula. I will give you this formula in the exam, so you don't have to memorize. So if we talk the same thing in terms of potential, BC as a function of time is given by you have a maximum potential. E power t over tau. So I think I made a typo over here. Q equal to C times E. Q over C. You can put like this, or you can put like that. BC equal to Q0 over C, like that. Q0 divided by C. Alright, so this is about the charge. Definitely if you use up your capacitor for a long time, the charge, it will be drained and it will come to 0. You have a maximum charge in the beginning. The current, the behavior is same as charging. The current will be maximum because the maximum potential will be at the beginning of the, this is the current I. So you have a maximum current in the beginning, okay, I0. And if you use up your capacitor for a long time, again, the current will be, like this. IT equal to I0 E. This is the behavior of a the current and charge the discharging circuit. And this is the, like, I told you that this equation can be derived from the differential equation. If you know differential equation, I showed you in the last lecture how we can use a differential equation to solve it. This is very easy for you. And because of time, I'm not going into detail, but the last time I already showed you in the charging case. So any question about RC circuit and discharging case? Okay, so if not, let me solve a couple of problems. I think I can solve one of them, and it is this topic. So it's very similar to the charging case, but in the exam you need to figure out whether the given problem is that for the charging case or discharging case. Okay. So over here, let's talk about this question. You have given the figure, differently given a circuit, and that has a battery and switch S, and you have a resistor and capacitor. Definitely is RC circuit. The switch S in the figure is closed at time t equal to 0. You turn on the switch. To begin the charging, initially uncharged capacitor off. The capacitance value is 15.0 microfarad. So you have turn on the switch and you charge it. And resistor value is given. At what time is the potential across the capacitor equal to the across the resistor? I need to find time at which the potential across the capacitor is equal to the across the resistor. And this is charging case or discharging case. Discharging case. I was looking for the problem that is for discharging case, but it looks like it's charging case. Do I have another problem for the discharging case? Doesn't look like. It's starting off. I'm gonna grab one problem, okay? Let me grab one problem. Discharging case. I was trying to look for the discharging case. I know this is the discharging case. Let's take a look at this one. Capacitor with the initial potential difference of 100 volt. I think this should be discharging. You have a capacitor, and that you have a potential difference of 100 volt, and is discharged through the resistor. It's a discharging case. It says discharge. So you have a potential. Let's say V1. V1 is 100 volt. 100 volt. You have a capacitor in the beginning. You have 100 volt at t equal to 0. Let's say you have a T1 equal to 0. At time T1 equal to 0, you have 100 volt. and it is discharged to the resistor. You have a discharge to the resistor, and a time 10 seconds. Let's say you have a time T2 equal to 10 seconds. You wait for 10 seconds. The potential across the capacitor becomes P2 becomes 1 volt. Okay? So in the beginning your capacitor is fully charged, you have a 100 volt, and if you discharge for 10 seconds, the potential drops to 1 volt. So discharging, right? You are draining your potential. Now, given this information, what is the time constant? I need to find time constant from this information. So you have to find A, tau, and a B, and let's think of your time constant first. You need to find a time constant. So, take a look at this one. Let me read this one. I need to find the time constant. Okay? So, according to formula, time constant is R times C. But I don't know what is R value, what is C value in the information over here. Right? I cannot use that equation to find the time constant. What I can do? I can use the formula for the potential, right? Because we have like potential value at different time. The formula for the potential is here. We can use this formula. Okay? If I have a time T1, it will be T1 over here. If I have a T2, I have to put T2, right? So let's use the this formula. A BC. Let's use for the T2. It will be okay, T1. Sorry for this. T1 E minus T1 divided by tau. I use this equation first. Let me use this equation. So T1, if I have a T1 value which is 0, I have the 100 volt. 100 volt. You have a E. T1 is 0, right? E power 0. So that gonna be 1. So basically it tells me that E equal to 100 volt. From one equation I have. From T1 I could get what is the E value. So yeah, let's use the T2. We see T2 equal to E power T2 divided by tau. Okay. Now voltage across the capacitor at time T2. Voltage across the capacitor at time T2 is 1 volt, right? Isn't it? I have a 1 volt. E value from the equation 1 I got 100. E T2 value is 10 seconds. Tau. From this equation, there is a only one unknown, that is tau. Right? Can you calculate tau? Yeah. It's very simple. Just that equation. And so if you want to solve, just take and divide over 100 on the both sides, 1 over 100. E power 10 over tau. I just take natural log on the both sides. It will be minus 10 divided by tau. So from here you can easily find what is the tau value. Tau equal to minus 10 divided by natural log of 100. Whatever the number, you will get the timing, the tau value in second. Tau value. The time constant, and you have a calculator. I don't have a calculator, so please get that number. Over here. Okay. All right. So any one of you guys got the number? So the answer says that 2.17. Please double check this number. Okay, 2.17. Okay. Okay. Great. So we got this number. And part B, I mean, we can wait. We can wait for 17 seconds. What is the potential difference across the capacitor if you have a time is 17 seconds? So over here, if you wait for time t equal to 17 seconds, what is the potential across the capacitor? I need to find that. Okay? I need to find that value. One thing, like sometimes you have to make a judgment. You started with 100 volt at t equal to 0. You wait for 10 seconds, the potential is 1 volt. Okay? Now, if you wait for 17 seconds, okay? I don't know what does the number look like, but I should get the potential value less than 1 volt. Do you agree with that? Because you are basically draining the potential, okay? It's a discharging case. If you get a number that's bigger than 1, then you have some problem with your calculation, okay? So I need to find the potential. Again, use the same formula. V, C, T equal to T3 equal to E T3 divided by tau. Just use that value. You have it is 100 volt and E, the T3 70, and tau value from here, you got 2.1, 2.17, and whatever the number you get, that will be potential in volt. So, it's a very simple calculation. According to answer, you're supposed to get 3.96 times 10 power minus 2 volt. Okay, make sure that you get that number. Okay, with this, I want to finish this long chapter, and I want to focus on another chapter, that is chapter 28. So we basically gone through electric studies. We talked about electric current, everything, Ohm's law, resistivity, everything about the electricity. And now we talk about the magnetism. Okay, so magnetic fields. This topic also a little bit longer, but let's try to finish in time. So the chapter 10, and it talks about the magnetic field. So we talk about first a magnet, okay, and the magnet is like something we have seen in our and from your high school also. The magnet is something that attracts a magnetic object, and magnet it has a two pole, north pole and south pole. Okay, so you have a magnet in the dipole, and so you have north pole and south pole, and they always come together, as I mentioned, last time whenever we talk about the electric dipole. Electric monopole can exist, but magnetic monopole doesn't exist. So over here you have a north pole and south pole, okay, north pole and south pole, and if you want to draw the magnetic field lines, the magnetic field lines start from the north pole and goes to the south pole. Okay, it's like that. It's a general behavior of magnet, and it's very similar to the electric field lines we draw. If you want to find the direction of magnetic field at any point, you need to draw a tangent. Okay, so if you want to find, let's say, magnetic field direction at this point, you draw a tangent. Okay, you will draw a tangent to this point. Okay, it's the direction of magnetic field. So the tangent to any point of these field lines gives the direction of magnetic field. It's very similar to the electric field lines, and the magnetic field lines also never cross each other. It's like the same thing. Okay, field lines, they never cross, because if they cross, you're gonna have a two direction for a vector at a point, and that is against the physics law. Okay, so magnetic field lines also never cross each other. Okay, so this is about the general information. Okay, and one very important thing that I want to tell, that Earth is a magnet. Okay, so I think you know about the compass, how the compass works. Especially for the navigation. Nowadays we have GPS, and GPS works pretty good. If you have internet, you can, even like a GPS device can work. Okay. A cell phone, I need like like a internet, but in a GPS device, it in a car it works even without internet. So basically, in the past, whenever like people are like traveling, especially like people from military, they have a device, it's a compass. Okay, and most of the time they used to have in a watch, and sometimes like it's somewhere here, and the sailor in the past, like if you are in you are in the ocean, like somewhere like a very water surface, and everywhere is water. You don't know where is north, where is south. In which direction you are navigating your ship. You don't know. So you need to know, taking a look at map, which direction you have to go. Okay? So basically, small device, a compass, you have your north, south, north pole, south pole, and basically you have a needle in which direction you are going. Okay? So this one is working because Earth has a magnetic field. Okay? Okay, North Pole and South Pole, they attract each other. So in the North Pole, so basically this which is pointing, you are going in the North Pole direction. And the compass is working because of the Earth magnetic field. The Earth magnetic field is very small. It is B value is very small. It's a micro Tesla. It's around 45 to 65 micro Tesla. So it depends on where you are. So in the polar region, you have a big field, but if you go to like this equatorial surface, you have a small valley. Or the geographic North Pole, geographic North Pole, North Pole. Okay, you have a South Pole over here, geographic South Pole, geographic South Pole, South Pole. Okay, and here the magnet due to Earth is aligned like this. Okay, it's a typical direction. You can. It's a South Pole and the North Pole for the Earth magnet. Okay, so basically they are same. The North Pole for Earth magnet is aligned closer to the geographic South Pole, and South Pole of Earth magnet or magnet due to Earth is aligned closer to the geographic North Pole of the Earth. Okay, they are not exactly like a vertical. They is a little bit tilted over here, and the value of this magnetic field is very small. Okay, it's not that much. 25 to 65 Tesla. It's a small magnetic field. Okay, and this value varies. Where you are. If you are closer to the polar surface or like a polar region, you have a higher value. And if you come to the some equatorial region, you have a small value. So it's like a gravitational constant. The G value we call is 9.8. This is very closer to the Earth surface. But depending on where you are, the G value varies slightly. It doesn't vary like the 9.8 becomes like 6, but it might be 9.4, 9.6. Okay, or you can have maybe 10 something. But the value is slightly different. Okay. So this is about the Earth magnetic field. And by any chance, do you know what is the origin of Earth magnetic field? Why Earth is a magnet? Just for curiosity, we always call okay, Earth has a magnetic field. And what could be the reason for Earth magnet? What is the giving contribution to Earth a magnetic field? Just for curiosity, anyone of you guys know? No? So if you, Google it, you will find the answer. But so Earth has inside the Earth you have a lot of magnetic material inside, and they are in a molten state. Okay, that is a source of we have a lot of nickel, iron, other some magnetic object, and Earth is going in the rotational motion. So that is the source of magnet. Okay. Anyway, so this is about the Earth magnetic field, and so a charged particle also experience force if it is inside the magnetic field due to a magnet. So let me talk about that. So let's say you have a magnetic field like this. The direction of magnetic field is aligned along this direction, and a charged particle. Let's say a charged particle moves along this direction, and it is moving with the speed of v, so that angle between these two vectors is given by theta, and this charged particle I call q. This charged particle experiences a force. This force is given by Fv equal to q v cross v. This is the force experienced by a charged particle in the magnetic field, and so this is the vector form. Force the vector. I can find the magnitude by just putting like a FB equal to Q V D sine theta. Okay, because you have a cross product, you have this is the magnitude of the force. Okay, so this is the force experienced by a charged particle in the magnetic field, and this force depends on angle. This force depends on angle between magnetic field and in which direction the charged particle is moving. So B cross B, it has a sine theta. So it depends on the angle. So let's take a look on this one. If the charged particle is moving along the B direction, magnetic field direction, what is the magnetic force? If charged particle, let's say, is moving along this direction, if it is going along the same direction as the magnetic field, what is the value of force? It will be 0, because the theta will be 0. If theta is 0, sine 0 is 0. Doesn't matter how speed, how fast the charged particle is moving, it will be 0. And if charged particle rest, then F equal to 0, right? If charged particle is at rest, the velocity is 0. If you multiply 0, your force will be 0. Okay? So these are some special conditions. So the maximum force gonna be there if charged particle move perpendicular to the field direction. If this is 90 degree, sine 90 is 1. Right? So that means you have a maximum force. Let me write down over here. So FB is maximum, and the maximum value is QVB, because theta is going to be 90, sine 90 is 1. These are some special case where you have to pay attention, and that's going to be also in the true and false question or multiple choice question about the force experienced by a charged particle in magnetic field. Sometimes it becomes 0, sometimes it becomes maximum. So if the charged particle is moving perpendicular direction, you have a maximum force, and if the charged particle is moving along the field direction, the theta will be 0, you have a 0 force, and if the charged particle is at rest, it will be 0 because velocity will be 0. Now, I am talking about the magnitude, but force is a vector quantity. Okay? So how to find the force direction? For that, we have to use the right hand rule, like in the cross product, right hand rule. And you might know it, like if you have taken calculus, you must know this one, okay? It's called right hand rule. You take this right hand and take right hand and go to the first vector. You have 4 fingers over here, you have a thumb. So basically, in the formula over here, identify the first vector. The first vector is like a V. Second vector is V. Right hand, align your 4 fingers to the along the first vector, and call your finger 4 fingers to the second vector like this. And direction of thumb gives the direction of force. So over here, your direction of force is out of whiteboard. So basically, your force is going to be out of whiteboard, and the vector rotation will represent like this. It's the direction of force. So you have, assume that you have an arrow that is coming towards you. Okay? The direction is out of the whiteboard. So this is how you find the direction of a cross product or force over here. And I already explained how to find the magnitude. Okay? Any question about this one? Alright, so let me talk about this problem and let's talk about this problem. So you have a proton and it is traveling with the speed, it is traveling at the angle of 23 degrees with the direction of magnetic field, and the magnetic field is given is 2.6 millitesla. So you have a proton. The proton has a charge is 1.6 times 10 power minus 19 coulomb. Okay. And it is traveling with speed. Some speed, but angle is 23 with respect to magnetic direction. And magnetic field is given B. It is some millitesla, 2.6 millitesla, 2.6 millitesla, which is 2.6 times 10 power minus 3 Tesla. There was some conversion factor over there because you have millitesla. It experiences a force of 6.5 times 10 power minus 70 Newton. So you have a force. Fb is given, Fb value is given. The magnitude of the force is 6.5 times 10 power 17, okay, minus 17 Newton. Now this was force that a charged particle experience. I need to find the speed of the proton. P equal to what? So you can easily use this formula. You have given the force, the charge is given 1.6 10 power 19. The B is given, theta is given. Can you calculate B? Yeah. It's a very, simple calculation. I just write down this formula and you use this formula. FB equal to Q. You can put like that. B sine. Everything is given. You can just calculate what is unknown. So everything is given. So that will be proton speed and its kinetic energy in electron volt. kinetic energy in the part B. Kinetic energy. The kinetic energy, you can write down kinetic energy. The kinetic energy, I just write it K. If you were 1/2 m v square, and you already know what is the v value from here. In meter per second. So you need to use this formula to find the kinetic energy because 1/2 mv square. And you need to know what is the mass of the proton. That's the only thing over here. The mass of the proton you have to know, and I also don't know on the top of my head. So in the exam you will be given. So let me take a look on the what is the mass of the proton. You can just use this formula. Mass of proton. Mass of proton. So in kilogram, 1.67 10 power minus 27. So mass of the proton is 1.67 times 10 power minus 27 kilogram times the velocity square. The velocity, whatever the velocity you get from there, you will have that velocity over there. One thing, whenever you calculate this way, is the kinetic energy, it will be energy in joule. Right? Energy in joule. Energy in joule. So if you want to find your solution in electron volt, what you have to do? You divide the answer by the charge of electron. Okay. If you want to find the electron volt, you divide the charge of electron. Charge of electron is 1.6 times 10 power minus 9. You divide that. Okay. Can you get this number first? We can try whether that's true or not. You have a solution for this in a B value. Anyone of you have the number for B?
4 times 10
4 times 10 power 5. Okay. Now, if you put this one over here, what is the 4 times 10 power 5? What is the number you get over here?
1.34.
1.34.
That's the negative 26.
10 power minus 7 or 6?
26.
26, okay. 26. It's a joule. It's joule. So if you want to calculate this one in a electron volt, divide by 1.6 times 10 power minus 19. If you do that, it will be in electron volt. Can you do that? 1.34 times 10 power minus 46 divided by 1.6 times 10 power minus 19. Oh, you have a 26 over here?
I got a negative 16 right there.
I think it's 16 because you have a square over here. You make it 10, so how much 27? So if you divide by 1.6 times, so this divided by 1.6 times 10 to the minus 19, what is the number you get? (1.34) times 10 power minus 16 divided by 1.6 times 10 power minus 19.
Negative on the 16. I got it.
Hmm?
The exponent, is that a negative 16?
Yeah, I must put 6.
Okay.
Okay.
I got 835.
835, okay. 835 electron volt, okay. So that means that's how you need to calculate the energy in electron volt, okay. Divide the charge of the electron, okay. Electron volt means the energy that is carried, and it's a electron was a unit in the energy. All right, so this is about the force experienced by the charged particle in the magnetic field. So over here I have another topic. This is the single charged particle. You have a single charged particle, and it is moving in the magnetic field. Now, suppose you have a current, which means you have like a large number of charged particles flowing through the wire. At that time, each charged particle experiences a force. Okay? Let's talk about that. So this is the force experienced by a single charged particle. But if you have a current carrying wire, that means current means you have a large number of charged particles, because like you have a charged particle, either electron or proton, okay, or holes. You have a charged particle that is flowing through the, and it is what the current. If you remember, current means delta Q divided by delta T. You have net flow of charge particle divided by time. It's a definition of current. Let's assume that the current is going this direction, I. So you have a magnetic field is like that. Let's say you have a magnetic field like this. And I'll tell you what that means. So in a vector notation, you have two ways to write the force or any vector like that. Let's say you have a B. What that means, you have a magnetic field that is coming out of the whiteboard. Arrow is pointing towards you. Okay? The B is out of the whiteboard. If you are writing in the plane of paper, it's coming out of the plane of paper, whiteboard. The second way of writing is B is into the whiteboard. The magnetic field is going into the whiteboard. So basically, this is the tail of the arrow, vector. Over here, you have a current carrying wire that is in the magnetic field. Magnetic field is into the whiteboard over here. Now, as I told you that if you have a current, then you have a charged particle flowing. Each charged particle experiences this force. Each charged particle experiences this force, and so you have a current like that. And if L is the length of this, wire, L, then we can derive, this formula. Force is given by I L cross B. This is the formula for the force. The force experienced by a current carrying wire is given by this formula. We can derive this formula, it's not that difficult, but for time being, I just skip that part. So you can expand this one because each particle has the force of this one, and you can and assuming that you have n number of particles, charged particles flowing, you can extend this formula and you can derive this one. One very strange thing over here. So if you want to write down the magnitude over here is given by I L B sine theta. Again, the magnitude of the force is given by this formula. Take a look on this formula. Force is equal to I L cross B. B is the magnitude is a vector quantity. L is the length of the wire. And if you have taken the physics one with me, or with any professor, length is not a vector. Length is not a vector. Length is like some number. If you talk about, what is the length of this guy? It's a 1 centimeter, let's say, or 5 centimeter. You don't have to give a direction. It's a scalar quantity. What you are doing some very interesting thing over here. You are making a scalar quantity a vector. Sometimes we do in the mathematics, to simplify the mathematics, we make a scalar quantity vector. And I don't know how many of you guys know. Area is also a scalar quantity, but we make it area vector by multiplying with the normal. Because area is vector, it's not a scalar quantity, but sometimes you need to make a area vector by multiplying the normal, because normal has the direction. You need to have some way to give a direction to the scalar, because the scalar is just a magnitude, right? So the difference between vector and magnitude, scalar and vector is scalar, you have a only magnitude, and vector, you have a both, magnitude plus direction. If you want to make a scalar quantity to vector, you need to find a way to give a direction. So if you have some area now, I think you will have done something for the magnetic flux or electric flux. It's an area. And if you want, area is like a scalar. So if you want to make an area vector, you need to give a direction from normal. So that, the magnetic flux or electric flux is given by E dot A. E dot A. If you have an electric field somewhere like this, you have an angle theta, then the flux is given by E dot A. But here, again, area is not a vector. But you have to put it like vector sign. It's a dot product between two vectors. Okay? Now I made this area vector by giving the direction of normal, because normal to the area is a direction. Okay? So don't be confused. Okay? Sometimes in mathematics we play a trick. Okay? And how an area become a vector? So it's not a vector, but we make it vector for simplifying the math. Okay, that is the motivation. Same over here, I have a length of the wire L is not a vector, but I made a vector. I need to give a direction, and I give a direction. The direction of current is the direction of this L vector. Now this vector, but the direction of this length vector is defined by the direction of current. Okay? So over here, don't be confused. The direction of L vector is the direction of current. If the current is going this direction, your length is going to be also in that direction. Now, I can find the direction of this force using the right hand rule. So, right hand rule I just told a while ago. If you have two vectors, the first vector and second vector, take your right hand and point your fingers from first vector to second vector. Now, my current is going this direction, my length vector is along this direction. One vector is like this. The second vector is going into the whiteboard. So it's like that. One is going up, one is going this direction. The first vector is length. So I need to take my right hand, first vector, right? The second vector is like that. The direction of thumb is towards me. My force is going to be F. The force on this current carrying wire is going to be along this direction. Okay? So this is going to be the force. I just use the right hand rule, okay? Any question about this one? I have one question over here, and I have only 5 or 6 minutes left. I wanted to solve this one. It is current carrying wire, and since the lecture is already in a heavy, so what I can do in the next lecture, I will revise very quickly this one and give an information about this problem. Okay? So with that, I want to finish the class for today. If you have a question, let me know. See you on Wednesday.